I'm going to show you the basics of doing a simple linear regression in JASP. In this video I'm using fictional scale data version 2. The data, or the link to the data, is available in the description to this particular video if you want to follow along. So in order to do just a simple linear regression, which means I have one y value that I want predicted by one x value, I'm going to click on regression. So you have classical Bayesian options. Bayesians are more advanced. We're not going to deal with that. We're going to click on linear regression. And this interface pops up here. I'm going to choose my y variable, which is the thing I want to be predicted. So let's say I want to predict this sum scale, which is the sum of these fictional items 1 through 20. I'll put it as my dependent variable. And I want to predict it from age. Okay, so I'm here trying to decide whether a person's age predicts their scale score on this data. And you'll see the information pop up over here. And what it's going to give me is a variety of information. With simple linear regression, we don't typically use these first two tables too much. Those are often used in multiple linear regression, which is beyond this video. For simple linear regression, what we're going to typically look at is just this particular table. We want to look at, this is basically a model it gives you by default with only an intercept in it, meaning assuming that the slope of the line is 0. Let's ignore that for now. Most people in basic statistics courses don't deal with that situation. What you would typically find if you did a simple linear regression and other software that's comparable here is just these last two lines. Okay, the first thing given here is the intercept. Okay, the second item given is the slope. It gives me the standard error for each of those. It gives me the standardized value of the slope. The t-values and the p's. This is the p-value for the intercept, which means that the intercept is non-zero. We typically don't interpret that or worry about it. This is typically the value we do worry about, as whether the slope happens to be non-zero. No statistical evidence of that, in this case, non-significant. So that's the information you would need. And again, the purpose of this video is not to go through the theory of linear regression. That's something that hopefully you have learned elsewhere already, or maybe at some point I'll add some videos that go into that, but just how to do it in JASP. And so the information you really need for a simple linear regression is in the last two lines of this, and we find non-significant. I'm going to just show you that there are a variety of options. Some of these only matter if you're doing multiple linear regression, which of course can be done in the same interface where you have more than one x. The model, we don't worry about those simple linear regression. Okay, statistics, if I go down here, what I may want to include is confidence intervals. And you will see when I do that, that I end up with, in that table, confidence interval around the intercept, confidence interval for the slope. Okay, so that's something that can be helpful. I may want descriptive statistics. Typically, that's something you should look at for all of your variables when you're doing a simple linear regression. You see that I have means, standard deviations, and so forth for those two variables popped up for me. So I don't need to go separately up to the descriptives to do that. Okay. Most of these things are things you only worry about with multiple linear regression. Okay. You may want to look at some of these things these things help you look at whether you've got outliers, meaning a particular data point that is far from the line, okay? And we only worry about that typically if we have a smaller sample and that data point is from the line in a direction that changes the slope of the line. It's what we call an influential outlier. And again, smaller sample that data point is different from the line in a direction that matters. And the first thing that statistics gives us, okay, is it basically gives us how big the residuals are, meaning how far the points tend to vary from the line. The distance from the line from each of the points varies in this range, and so forth, okay? And you may want to use some of these statistics to tell you whether any particular points are particularly far from the line. This one here, some people look at it's like more than 3 standard deviations from the line, and you can see this case-wise diagnostics doesn't have anything here. Means there's not any points that are quite far from the line to worry about. But there are a lot of things to think about and do with worrying about whether you've got an outlier that's affecting your results beyond the course, beyond this course, or this particular video at any rate. And but you do want to often look at the plots. Okay, the plots are the simplest way to determine whether the assumptions of simple linear regression are met. One being, are there outliers that are causing influence? Another assumption that is important is, are the residuals normally distributed? That's important. Another important assumption that you need to examine is whether there's curvilinearity in the data. In other words, was fitting a line through this data appropriate, or would a curve have been better? And then the last thing that's really important to look at is whether there's something called heteroskedasticity, which basically means that points fit better to the line for low values of x than for high values of x, or vice versa. All these things are easy to look at with plots. And for simple linear regression, okay, the easiest thing for simple linear regression is to look at your residuals versus your dependent value, okay, and your residuals histogram. So I usually, for simple linear regression, suggest clicking this box and looking at those two. So let's pop over there. You'll see those pop up. Now, what this is showing me is whether, when we look at this residuals versus dependent, it's showing the residual is how far a point is from the line. We're going to look at that with respect to a specific y value, and we don't see any pattern to that. We don't see that for bigger y's, points are further from the line, or anything like that that's problematic. We're looking for this to basically see whether something like that happens, okay? Whether we get points further from the line for lower or higher values of x. That would be heteroskedasticity. We look to see whether this is a curved shape. If this was curved, it would mean I should have fit a curve to the data. Instead, the data is not linear. So that's the second thing we look at here. The third thing we look at is whether we have points really far from the line that we think might have pulled the line the wrong direction. And here we don't see anything like that. The other thing we do is we look at a histogram of the residuals right here, and we want them normally distributed. Again, the residuals are the differences between the true y values and what the y value was predicted to be if the line was perfectly through the data. Or, in other words, how far a point is from the line in the vertical direction. So we look at this and we see roughly normal. It's not hugely non-normal. Obviously, it's not perfect. You might say it's a tiny bit skewed. We are looking for data for this to be significantly not normal. Maybe there's 2 big peaks that are separated, or maybe it's extremely, extremely skewed. In this case, this is pretty good. It's pretty close to normal. It's roughly bell-shaped, centered in the middle, and it looks okay. And because those things are met, it means we can interpret our results without any concern.